Well, good afternoon. It is once again, well, maybe there it is. Yes, Comp 422 and Comp 620 Internet Privacy and Security. Today we're talking about network security. Maybe we will. Okay. Reminder that there is an online assignment due Tuesday of next week, October 8th by noon. Yes, and you have to sign into my server. You also have to go out to the dark web. We'll talk about that today and find some information. You'll need to download the Tor browser, which I'll talk about. By the way, this assignment appears in Blackboard in two parts. One part for 60 points is the information from the dark web and from the JavaScript attack that you have to do. The other part is the 40 points from logging into the system. That's separate. That's scored online automatically. And so I'm just going to copy that, paste it into Blackboard, score what you have in Blackboard. And I will combine them sometimes later on, but it makes the scoring easier. Okay, networks. Now, networks have been around for longer than you probably think. They built a optical telescope long ago in 1793, Claude Chappé. If you ever watched the movie about the Count of Monte Cristo or read the book, during the book, he bribes the telegraph operator to send a false message. So it's been out there for a while. Electrical telegraphs came around 1844 with Samuel Morse, famous for Morse code, and then Alexander Graham Bell. We are in the Alexander Graham Hall right now, but it has nothing to do with Mr. Bell. He invented the telephone. Internet followed 100 years later in ARPANET and started coming out with Ethernet and TCP, and I was there. And eventually, in 1991, Tim Berners-Lee, now Sir Tim Berners-Lee, came up with the web idea, and that's been going for some time. By the way, today we're talking about networks. If you know all about networks, you can kind of fall asleep, but the purpose is to give you some background in networking. So when we start talking about network security issues, you'll understand how the network works and how these security attacks occur. Okay, whenever you talk about networks, you have to talk about layers. There are these 7 layers of the OSI model. So there they are. That's not too important for this class. But basically, you put in a message in at the application layer. By the way, HTTP is an application layer protocol. It's hypertext transport protocol. And it goes down, gives this layer, each gives it to another layer, gives it down to the physical layer, which actually squirts the bits across to intermediate or many intermediates. And it only goes up to the network layer. The network layer is responsible for routing, figures out how to get it there. It finally gets to the end, goes up to the next one, and gets to your application. I like this analogy that, say you're going to send a letter to a friend in a distant city. You don't have to worry about how to find there. You put their address on the letter and put it in your mailbox, and it gets there. The post office takes it. They don't know how to fly airplanes. That's not their business. But they take the letter, they put it in a bag, give it to the airlines and say, fly it to this city. And the airline flies it to that city, gives it to the post office in that city, who then looks at it. They know where that street is, and they put it in a bag and take it to your friend's home and deliver the mail. Each layer adds some additional features. And you just talk with the post office, and the post office talks to the airline. You don't have to know anything about the airlines. The airlines, again, do their job, pass it off to the post office, and send it to your friend. In the network world, you have your data, and each layer adds another header to it. You keep adding headers, top of headers, top of headers, providing information about what they're supposed to do with this data when it gets there. Some of the lower levels also add a trailer that is often used to check for errors. Okay, now you can interconnect networks in multiple ways. I'll talk about that for a few minutes. At the lower level, at the physical layer, you have repeaters. At the data link layer, you have bridges. The network layer, you have routers, and you can also have routers up at the application layer. So let's talk about those briefly. Repeaters, again, are at the physical layer, the very lowest. All a repeater does is copy the bits that come in. It copies them. Any signal that comes in, it's just an amplifier. Sometimes you need an amplification to get the signal from way over there to way over here. Also, you might have a hub or a device that has a stream of bits coming in, and it sends the bits out on multiple different wires. Every bit, including collisions, if you have an Ethernet collision, and the Ethernet is a very popular network protocol that people use on wires. And so that's used a lot for local area networks and small networks. If you're going to go a long distance, they use other more advanced networking protocols. An Ethernet can go up to 1,500 meters, no more 4 repeaters between them. You can have repeaters. And an important thing to note is that they are invisible to the network. You can plug these things in. It just provides an amplification. You can plug things in with repeaters, and network doesn't really know they're there, particularly the computers that use it. Again, you can have hubs. A hub is a very simple box. You can buy probably the cheapest network box you can buy. And it, again, bits flow in through one of the ports and all flows out through all the other ports. It just connects one port to all of them. Pretty simple. And you use these things at home if you have a bunch of devices. And by now, everybody has lots. I've got 2 computers, 2 printers, wireless, all these things going into boxes. Actually, more than 2 computers. Bridges operated slightly different. Bridges receive a whole frame. In other words, you're going to send a message on the Ethernet. Messages are broken up into pieces that they call frames. It's just a chunk of the message. One large message will be broken into multiple frames, and they send each frame across. A frame is received by the bridge, and if it receives it correctly with no errors, everything looks good, then it will forward it on to wherever it's supposed to go. Because it has to receive the entire frame and then send it, there's a slight delay. Now we're talking nano or microseconds here, so there's not much of a delay. Whereas a repeater doesn't have a bit goes in, a bit goes out, there's no delay at all. With the bridge, there's just a little bit of delay, not much. And again, they're invisible to the network. The interesting thing about bridges is that they learn how to transmit the information to the other side. A bridge has a connection to multiple wires, and those bridges can be connected to other bridges, which are connected to other bridges. It all forms a tree if you're a computer scientist, no loops, and the bridges learn where the other computers are. As they send things out, they look at messages coming from either side, and if they see a message coming in from one side, they go, oh, that computer must be over there. So if they see a message coming from the different side going to there, they go, oh, I know that computer's over there, and they send it over there. Broadcast, you can send a broadcast. Broadcast goes to everybody. This is a message you can send. I want to send this to everyone. And of course, broadcasts go through it. You don't usually have bridges in home networks, but they're used here at the university quite a bit. And again, they're invisible to the network. They're invisible to the computers that use them. You send something out on the network, and if it has to go across to another network, it bounces from bridge to bridge until it gets to where it's supposed to go. The bridges handle that automatically. The next layer up are routers. Routers are the network layer. Again, the network layer is responsible for routing, for getting things to the end. So again, they are store and forward. They receive a packet and then forward it to where it's supposed to go. Interesting thing about routers can operate on different types of network. You can receive something in on a token ring network and send it out on an Ethernet. It does that. Also, they're frequently used for connecting networks together. In other words, if you have a home local area network and you're connecting to a wider network, you have a service provider, then your router will connect to the service provider. Sometimes routers are called gateways. They are a connection to them. Yes, we have a question.
Bridges, that's another way of saying switch, right? bridges and switches are the same thing? Is that,
Yeah, there's all sorts of names out there. I think a switch might be a router because a switch kind of implies it makes a decision. Of course, bridges do make a decision, but you don't know. I'm not sure where switches are in the whole scheme of things. There's lots of names, gateways and routers, maybe a switch. Again, the router is important. The router is visible to the network. The computers have to know the router is there. If your computer is connected to a local area network, and the local area network is then connected via a router to the internet, your computer has to know the router is there. If you want to send a message to some other computer on your local network, it just transmits it and it gets there. The bridges and hubs take care of that. If you want to send something to the internet, you have to send it to the router, and the router will send it to the internet. So it is visible. You have to know that there's a router there, what computer it is, and how to send things to it. Again, lower level things are invisible, but the routers are visible. All right. There are multiple names for computers. They're used at different levels. The highest level are the internet names, and those are there just for humans. You might have a name like garfield.ncat.edu, and they're alphanumeric. They're usually words separated by periods, and they're intended for humans. They're supposed to be easy for humans to remember. And then in Internet Protocol version 4, you have a 32-bit binary number that is the internet address. It's usually written as 4 decimal numbers separated by periods. Each number represents a byte. Here at A&T, everything starts with 152.8.something.something. Those are internet addresses, and they map to internet names. And then there's hardware addresses. And Ethernet addresses are 48 bits long, and they are built in. When you buy a Ethernet device, it has an address built in. Whenever you buy a laptop, if it has Ethernet port, yep, this one does, then it has an address built into it. It knows what that address is. If you have, same thing for some wireless devices. Addresses are built in. And since they're 48 bits, gives you a lot of numbers to choose from. They don't have to repeat. So, and the hardware only uses the hardware addresses. If you are using your Ethernet and you want to send a message to another computer, it will send it over the Ethernet, and it gets there if it has the proper hardware address. Doesn't matter what internet name, what internet address your destination has. You have to know the hardware address to get it there. By the way, the hardware addresses are sometimes known as the MAC addresses or media access control. That's the layer that it works on. Internet Protocol version 6 is the latest Internet Protocol. It's been around for a couple of decades now. It's slowly replacing Internet Protocol version 4, very slowly. It fixes a lot of network problems. One, addresses are 128 bits. The internet addresses are 32 bits. Well, any computer scientist should know if you have a 32-bit number, that gives you 4 billion possible values. Well, I've got multiple computers in my home, more than just one. There are 8 billion people in this world. There's not even enough to have everybody have one address. Fortunately, Internet Protocol version 6 has 128-bit address, lots of space for everybody to have their own address. The addresses are written as hexadecimal numbers. You write 4 hexadecimal digits to represent 4 times 4 is 16-bit values. For each hexadecimal digit, you should know this by now, each hexadecimal digit is 4 bits. So you have 4 of them at 16 bits written together, and they're separated by colons. And sometimes there's lots of zeros in there. If you want to omit the zeros, you can just put a double. And if there's leading zeros in a number, you can skip those two. So it makes it easy. So those are Internet Protocol version 6 addresses. And as we'll talk about a little later, version 6 has several enhancements. Well, that's why they made it, of course. It is better than not a lot of systems. If you have Microsoft Windows or Mac OS in a local area network, by default, they will use Internet Protocol version 6 to talk to other computers on your network. But most networks connections often, ooh, hang on. I'm sorry. I just turned around and looked. They're not, this is right. Stand by. We're going to see why we can't get these things. Kind of like the joke, but because, okay, folks online, you probably don't see this, but we are going to take a break here. Find out why this is going to. Okay.
I sent you a message privately.
Oh, yeah. It's really hard to read messages while I am doing the lecture. Okay, I'll reply to you after class. Sorry.
Okay, thank you.
Okay, let's okay, we're gonna get back to do that.
Yes, it's freezing, it's not frozen. It's probably something.
It's frozen, all right. Yeah, freeze. Why is it freeze? I wonder how I unfreeze it. Let's hang on. Here, dear. Well, fortunately, you have one. You don't need to see it twice. It's not in stereoscopic or anything. Okay, we'll just go along. Folks online. Oh, did I share my screen with you? Maybe not. Stand by. Okay. Back, everybody online can see it. Folks in here can see it. All right. They can also see more, but yes, well, hey, folks, if computers were all that easy to use, we wouldn't have a job. All right. Now, as I just mentioned, we have internet names, internet addresses, and hardware addresses. It's got a map between them. In other words, when you go to a website, you type in www.acme.com. But the network doesn't, as I mentioned, the hardware only uses the hardware addresses. So you got a map between them. Internet names, the readable versions are mapped to internet addresses through a domain name server. You send a request to the domain name server, say, what's the address for this name? And it sends it back to you. Easy enough. Internet addresses are converted to the hardware addresses using the address resolution protocol. Okay, and we'll just talk about both of them. If you look at the bottom of any sort of network box, you'll usually see the MAC address there. It's like 48-bit value, tells you what it is. And again, the MAC address are usually built into the machine. That is the address, you can't change it. And here comes our first question for today. So, got your cards? Anybody need a card? Okay. Whoop. Bye. All right. D is a very popular answer here and on the internet. I hope the answer is D. Yes, the answer is, everybody can see the results, all of the above. But unfortunately, it's wrong because the question asks, computer on the network needs to be aware of what? They need to be aware of routers. Routers, not all of them. Was the answer C? Well, the answer is C. The answer is C. Very good. Routers, you don't need to worry about hubs. You don't need to worry about bridges. And of course, you should be good students by now. You've been at the student thing for a decade and a half. If two of them are wrong, then the answer can't be all of the above. It must be the other one.
Said D on both sides.
Nope, not D. Answer is C. Sorry, answer B is C. Nope, routers. Doesn't care about hubs. Bridges operate automatically. Just routers. Computers have to know about the routers. Okay. Ethernet, the hardware. Ethernet. We got, plugs, wires, with Ethernet cables. They, Cat 6 or Cat 7 these days. Ethernet uses a 48-bit address, usually shown as 12 hexadecimal digits, because you all know by now there's 4 bits in hex digits, so they're all built with a separate one. And then there's a broadcast address to send to everybody. And again, you have to use the MAC address to send something. So your computer needs to know the MAC address to send a message to anything, even to the router or to another computer. So it needs to do that if it's going to send something to a computer on the same address. It needs to know the MAC address of the destination if you're going to send it to a computer on your same network. If you're going to send it to a computer on a different network that's going to go off on the internet, then you have to know the address of your router so you can send it to the router. The Ethernet uses the hardware address, so you got to have the hardware MAC address. MAC address and hardware address are the same thing. So we have the ARP protocol, which is really easy. It just broadcasts the message out to everybody and says, who has this internet address? And then everybody gets it because it's a broadcast. They look at it and go, that's not my address, and they ignore it. But that one computer out there who has that address says, oh, that's me, sends a reply saying, here I am, this is my MAC address. Pretty simple. Requires a broadcast. And again, if you've got hubs and bridges, the ARP request to go right through them because they don't care about that. All right. Now, I'd like to talk about security after a while. ARP poisoning is a mechanism for maliciously changing addresses. Again, when you send out a request to all computers, say, who is this? Well, if you have a malicious user on a machine, they may be waiting for that message. And as soon as their computer receives that message, they'll send a request saying, oh, I am that address, even if they are not that address. And so if your computer gets that false reply, ARP reply with a false address, when it wants to send something to the destination, it will send it to the malicious address because that's what it's been told is the MAC address for that destination. So when it gets to the malicious user can basically do whatever they want with it. The typical thing they'll do is they'll record what the information is, forward it on to where it's supposed to go, or respond as if it was going to where it's supposed to go, and put in a false reply. So the victim doesn't know. Your computer keeps sending things off to where it thinks it's going, but it doesn't go there. It goes someplace else. There are defenses for commonly used critical services, particularly like the hardware address of your router. Frequently, you send things to a router if it's going off your local network. I don't know about your traffic, but most of my traffic in my network goes someplace on the internet. Occasionally, I'll send them into a printer, but most of the stuff goes off network. So you can put those into your ARP and say, this is the address for this destination. You do not need to ARP for it. You need that address. Here it is. Don't change it. It's always that address. And that way, nobody can change it. It's read only. If another computer tries to send an ARP poisoning message, say, change that address, it won't change it. Then sometimes you can check the address against the DHCP server. DHCP is host configuration protocol. D for something, whatever D stands for, it doesn't matter. When your computer starts up, it sends out a broadcast message looking for DHCP server saying, I'm here, what addresses should I use for my computer? And DHCP will send back a response saying, oh, here, use these addresses. Sometimes it always gives you the same address. Sometimes it just picks an available address and sends it to you. So it changes every time. You can, when you get this, check against the server, see where it thinks the address should be. Internet Protocol version 6 recognized this problem. One of the reasons they try to improve Internet Protocol version 4 with version 6, it has the Secure Neighborhood Discovery Protocol, SCND. And that is a much more advanced protocol. It uses encryption, it uses certificates, uses public key encryption to ensure that the message it's getting comes from the correct source. So that helps prevent our poisoning. In the Ken Williams opinion, I just don't understand why computers are sitting there with version 4 and they get an ARP reply that says, oh, change your address to this. Why they change it? I mean, yes, it's possible that somebody unplugged the computer and plugged it in someplace else, and maybe it has a different MAC, but that so rarely happens that once you get a reply, you stick with it and not change it. But anyway, that's how it works. Some systems use random MAC addresses. They will create a MAC address. I told you in the beginning that MAC addresses are fixed and don't change. Well, some devices, particularly mobile devices, might recreate new MAC addresses. As they move to a new network, they'll create a new MAC address. It doesn't matter then because when they're connected to a new network, and it's connected to a different connection point, doesn't matter what it was before. This connection point only knows them by that one address. So they use a new MAC address. Edward Snowden, if you remember several years ago, he was an NSA worker and then defected, put a lot of information out on WikiLeaks. I think he's living in the Soviet or Russia right now. Nobody else wants him. And he says that they were tracking the movement of mobile devices in cities by monitoring the MAC addresses. And then sometimes they will use a hash to try to maintain anonymous use. Okay, internet names. Let's talk about internet names. Internet names, again, are for humans to read. They have a format starting on the right. It's a type. That is what type of organization. Is it .com for commercial organization, .org for volunteer or other organizations like that, and a whole list of them. In fact, I have a whole list of them. You can see there's .com, there's .org, there's .net, there's .name, there's .mil, .gov. Those are the popular ones. Also, country codes are very popular. In most of the world, the last couple characters of an internet address are the country code. So you might be in .fr for France, .uk, or .de for Germany. DE, Deutschland. So where we go? Yes, that's the type. Then there's the organization name. For edu is for educational. We have ncat.edu. A host is the computer name, usually 3 parts. www is not required for servers, but it's been used a lot by a web server. So it's become the standard for where you put a web server. You call the host www, and so www.acme.com would be the web server. You can also have a subnet in there. You can divide your networks into subnets. AT&T does not divide its network into subnets that you see as far as the names. By the way, the names are case insensitive. That means they can be upper and lowercase. It doesn't matter. So when you type in a URL, the computer address can be upper and lowercase. Sometimes the file names are case sensitive, but the computer name doesn't matter. Also, in emails, it's at, wherever you go at, it can be upper and lowercase. Some people get really picky. It's lowercase. No, it's not. It doesn't matter. And where all these names come from is from the Internet Corporation for Assigned Names and Numbers, ICANN organization. And they are an organization tasked with distributing names. By the way, I don't know if they charge for names. There's a lot of intermediates. If you want to get an internet name for your server, you can go to some company and they will sell you a name. Comp 422, Comp 620 online cost me $35 a year for that name, though I don't think CAN actually charges anybody for it. Okay. Domain name servers go between internet names, human names, and internet addresses. It's really simple. You just send a message to the domain name server saying, I want the internet address for this name, and it looks it up and sends it back to you. All domains, all networks have to have a domain name server, or their internet service provider has to support it. So if you have your own, like ncat.edu, it means NCAT must have a domain name server. Somebody who knows all the names, some system knows all the names of all the computers and all their addresses, so that a distant computer can send a request to the domain name server at this domain and say, what is the address for this machine? You can get it. Now, maybe they don't know all the addresses, but it will do a lookup through other servers to find it, which I'll explain in just a minute after we answer this question. Oh, hang on. I think it works where you want it to. There it is. Okay. All right. Poisoning. There you go. Or the proper orientation, looking at it yourself does not count. Even if you have it turned front. There it is. You want to make a vote? There you go. You like it there. Now you're looking at somebody else's because they're all different. You should notice the particular cards are all different. Everybody's. All right. C is very popular in class. A is most popular online. It always amazes me that we get different responses. All right. What is the proper answer? Corrupts address? No, it doesn't corrupt address in the domain name server. We'll be talking about that. That's not ARP poisoning. Kills an ARP server. That sounds cool, but that's not what it does. Nobody thought it did that. Okay, it's down to these two. Gives an invalid MAC address for a given IP address. Yes. Gives an invalid IP address for a given MAC address. It's C. It's going to give an incorrect MAC address for a given. You send out a request saying who's 152.8.244.1, and the one who has that number sends it back and says, here's my MAC address. Our poisoning is when you do it. Stop. Sure. So it's okay. Stop sharing. Let's go. All right. Everybody got that? Then moving on. Maybe. All right. Domain name servers are a global operation. You can get the name of a computer in some foreign country. Actually, Comp 422, Comp 620.online is not in the United States. It's in England. It's cheap. Got it. Okay, so they're hierarchical. And they go, of course, right to left on the hierarchy. There is a .com server, and it is the responsibility of the .com server to know the IP addresses of all .com systems, big server. And there's a whole bunch of them out there. These are repeated. There's lots of servers across the country, across the world doing this. So there's also, of course, servers for each corporation. You can have subnets, and each one of those, they know all the computers. So here's a animation. I want to send a message to www.acme.com. That's not on my same network. So I send a request to my domain name server, which has never seen a request for acme.com before. It doesn't know what it is. So it sends a message up to the root for .com. This is .com. What is www.acme.com? This is, okay, I don't know, but go look over here. Go ask this .com server. The .com server goes, oh, I don't know, but you can find out by asking the DNS.acme.com server. Here's the address of that server. So now that I have the address of the DNS.acme.com server, it knows the address because it's responsible for knowing all the addresses in its network. It sends back a request, which it then sends back to my computer. Easy enough? Kind of went around. Now, once you found an address, once your computer gets the IP address, it saves that. It caches that IP address. There's a list of IP addresses. You can print out there's a command to print out all the list of addresses it knows. There's also an ARP command. You go to command.com and just type in ARP, it will tell you what does it know. There's also one from IP addresses. So it saves them. This makes it a lot easier. So once you find an address, you don't have to go looking for it every time, because that was a lot of messages. Once you know what the IP address is for www.acme.com, you just save that and use that from now on. And likewise, the domain name servers save things, so they don't have to go asking. So next time, say you want to go to ftp.acme.com, you send a request to your local domain name server and say, what is the IP address of ftp.acme? It doesn't have to go on. It knows now. It has saved the address of the acme.com domain name server. It sends a request to that one. That one, of course, knows it because it has to know. It sends a request back and sends it back to you. And now you've got that address. So it's much faster. Of course, if you asked for it again, it would know because it's already been that way. There are multiple ways to attack the domain name servers. Some of them have been very successful. Originally, when they first built the internet, they just didn't think about security. That wasn't high on their list of needs, and so they didn't build anything into this. In fact, the whole internet was built without the concept of security, which is why there are so many difficulties with it right now. Internet Protocol version 6 tries to fix some of those, but there's still many. Sometimes you can have a computer which will pretend it is a domain name server. It's not a real domain name server, and it will pick up things going to it and may reply with false information. Or it can send false information to the domain name server. Computers have to tell the domain name server who they are, and sometimes machines will falsely tell the domain name server who they are. And now it has the wrong address, which means, of course, if you send something to www.acme.com, it will really go to www.evil.com, because that's where it's been routed to. And even though your computer appears to be doing everything correctly, it's going to the wrong site. Another question, what do these domain name servers really do? Well, one more. No, it's been bad. I'm getting ready to work for the Red Cross, and boy, they are going crazy with this flood. Okay, well, we have a variety of opinions. C is popular. Let's look at the answer. Okay, domain name server converts MAC addresses to IP names. No, nothing does that. IP address to IP names. No, it's backwards. Actually, it's IP name to IP address. That is C. There is something called a reverse DNS lookup, which does B, IP address to name, but that's not what we're talking about now. That's only used if you're looking for where something is. And then IP name to MAC address. Nope, nothing does that. Okay. All right. There are a bunch of security improvements to the network that make it more secure. The domain name system security extensions, DNSSEC, are updates to the domain name system to provide additional security. They encrypt messages, they use digital signatures to verify it. Yes, based on what you understand about encryption and digital signatures now, you can imagine how you might make this system more secure. If everybody had the address, the public key of your domain name server, you could send a message to it, it could decode it, nobody else could understand what it is, they couldn't reply, it would make it much more secure. And in fact, that's what they do. There have been multiple distributed denial of service attacks. We'll talk about those a little bit later on. They're coming up. And they've attacked some of the IP addresses and domain name servers, trying to overwhelm some of the systems. You look at the volume here. That's 2.5 terabits per second. You've got kilo, 1,000, mega is 1,000,000, giga is 1,000,000,000, tera is 1,000,000,000,000, 1,000 billion or 1,000,000,000,000. So that's a lot of data. That's pushing a lot of bits around, trying to Google, of course, is big. That's for 6 months until I finally killed that sucker. Amazon Web Servers. Amazon Web Server provides not just support for Amazon, but a lot of companies use the web server provided by Amazon. Amazon sells web services. If you want to have a website, you can put it on a Amazon system and they will support it for you. They're one of the largest web server providers. And again, lots and lots of bits going out there. Here's what it looks like. You're going along. This is the bits per second on your network. La-di-da, not much happening today. All of a sudden, pow! Imagine you are a network administrator. All of a sudden, this jumps up to, what is this, 1.35 terabits per second. And you're going, what's happening? And then it comes down. Oh, not all the way. And then comes down. Okay, so that's an attack. All right, let me talk about the dark web. The surface web are those systems that you can see and easily get to. Examples here, Google, Wikipedia, Amazon, Bing, those things. And then there are sites that you can get to if you know the address. For instance, ncat.edu, the Blackboard system. Blackboard is accessible from anywhere, but you have to have a password to get into it. You have to have your student ID and a password to get in. It's not really available to everybody, but if you have a password, if you're an A&T student, you can get into it. A lot of those systems out there. And then we have the dark web, which is out there that you don't know where it is. They don't know who you are, but you can still communicate with them. It uses, they are called onion sites, and they use the onion router. They have websites that end in .onion instead of your .com or stuff. And they use the onion router, TOR. The Tor software allows you to connect to those systems. Through the onion routing, they hide where these systems are. You don't know, can't find out where they are. They don't know who you are. We'll explain how that works now. They link to multiple. If you go on the dark web, you can look for the hiddenwiki.com and find out all sorts of, there's no real Google for the dark web because nobody really knows what's out there, but there are lots of lists of sites. So you can go to one of the websites that lists sites that they know about and click there and go to those sites. And sometimes those sites will list other sites and you can go around looking for things. Onion routing was developed by the US Navy, interesting enough. And it routes things and everything is encrypted. It keeps the source and destination. Each repeater, you bounce from multiple routers, regardless of actually how you might want to get to that site. It goes through multiple routers. And your computer encrypts things and sends it to the first router, encrypted with the first router's public key. First router gets it, decrypts it, and inside that is a packet going to another router. And so it sends it to that second router with its public key, which then gets it and decrypts it and looks and gets to a third router and sends its public key and bounces around as many times as you feel is necessary. until it gets to a router that sends it to the final destination. The destination knows what router it came from because it came from that one. But that last router only knows somewhere it got a message, doesn't know who it was, it knows where the router came from. The first router knows that you sent a message, but doesn't know where it was going because all that was encrypted. It's encrypted, kind of encrypted. So here's the concept. If you want to send a message, you send it to router 1, encrypted with router 1's public key. It decrypts that and finds inside there a message going to router 2. So it sends it off to router 2, and it's encrypted with router 2's public key, even though it doesn't know what it is. Router 1 doesn't know where it is or where it's going, but it sends it off. Router 2 gets it, decrypts it, finds a packet in there, says, oh, going to router 3, sends it to router 3. See, that message is already encrypted. Router 3 gets it, it can decrypt it and says, oh, this is where you want to go, and it sends the message there. So the site only knows that it came from router 3. Doesn't know where that came from previous to that. Each one might have tried to keep track of where they were. So each message is wrapped in another one. If you want to use the Onion router, you need to get the Tor browser. The Tor browser is easily acquired through the torproject.org download. You can go up there. Once you install that, you have to connect. It's pretty simple. And if you want to go things, there's a switch, use Onion only. There are, besides Tor browser, there's other anonymous operating systems that try to hide things. There's Unix. I think it's Unix. That's how you pronounce it. It's a version of Linux, Debian Linux, and it routes things using the Onion routing system. So it tries to keep everything secure. For the class, you have to go out and look at something on the dark web. Be careful if you're going to go out to the dark web. Now, the site you have to go to is just a forum, bulletin board system. There is a posting that I posted out there with the name Comp 422, Comp 620. It's not a very discreet name. I should have thought of a name but anyway, you won't miss it. Look there. There's a list of numbers and words. The words happen to be from the top 100 passwords, but the number is your last 4 digits of your university ID number divided by 1,050 and take the remainder. So you take your ID number, last 4 digits of your ID number, mod 1050, and that gives you a number. Remember that number. Look for that number on the list, and you find it. Next to it is a word. Put that word up in Blackboard, and you get full credit for that. I did the weird thing, so it's a little harder to trace back to who that was. If somebody sees the numbers, it's a little difficult, not terribly difficult, but a little difficult to tell what was your number. At least there are multiple opportunities. Questions about that? And be careful out there. Yes, drugs, sex, rock and roll, all of which are available on the dark web. It doesn't mean you should go out and do that. You know, it's interesting to look at the dark wiki and see what's out there and you go, whoa, look at that. But then stay away. Don't get yourself into trouble. So do that. Why are we doing this? Just to let you know it is out there. This is where people sell IDs. If somebody says your ID was stolen and they found the information, they were looking on the dark web. Places in the dark web sell ID information. So if somebody steals your credit card number, basically they'll break into a company's server and they will get a list of social security numbers, credit card numbers, information like that. What do they do with it? They put it out on the dark web and sell it. Sell it to anybody who wants to buy that information. So it's out there. Don't buy it. Don't get yourself into trouble. Okay, good enough for that. It's real simple. All you have to do is look at one site, the Blackboard site. It's very simple. Or it's a bulletin board. It's a forum. Look for one forum that is the class name and get the information that you need. Easy enough. Okay, moving along with networks. Again, we're just covering the background of networks so you understand how they work in general so that you can, so we start talking more about some of the network security problems, you'll understand how the networks work. Okay, you can divide networks into connectionless and connection-oriented. An easy way to think about this connectionless, connection-oriented, a telephone call is connectionless. You put in the number, it forms a connection to wherever you're going to talk to, creates a connection to that. You talk with them, everything you say goes across that connection, comes out the other side, whatever they say comes back, goes to you. And when you're done, you hang up, break the connection. Mail, letters are connectionless. You have to put the full address. If you're going to send 3 or 4 letters to the same place, you have to put the address in each one of them. You only have to put the phone number in once, and you can talk for as long as you like. With the letters, you send multiple letters. Each one has to have the full. Each one is set separately. The post office doesn't combine them. So if you send multiple letters to a friend, they may get there in the same order that you sent them, or maybe not. And it's, the post office, led by Louis DeJoy of Greensboro, doesn't always work as well as you would like. So if you put a dozen letters in the mailbox to the same person, or put one a day, sometimes my wife goes away, I'll send her a card, one a day, put one a day in the mailbox. They don't always arrive one a day when it gets to the location. She might get 2 one day and none the next day, or I get them out of order. Networks are just like that. The internet protocol. This is the protocol that runs the internet down at the network layer. This is the low level of the internet, lowest of the internet layers. It is connectionless. It's what they call a best effort packet network. That is, it tries to get all the packets to the destination. If it doesn't get there, that's too bad. It's not its problem. It tries to get them there if it can. If it doesn't get there, it doesn't worry about it. Packets might get there out of order. They might be lost and never get there, or they might be corrupted in some way. Some bit might be changed before it gets there. Internet protocol doesn't worry about those things. All those things can happen. By the way, the packets are called datagrams sometimes. If you see that word, it's datagram. Again, it uses internet addresses to route these things around. So if it goes from network to network, it sends it on the source. It has to use the MAC address of that computer, sends it to the first network, puts a header on that, sends it to the router using the IP address of that router, sends it to the next one, each time wrapping it up with a new header, putting it on a new address, going to different physical networks. So that's in the protocol. It's sent. They're all these packets are sent, bouncing across the network from. There's something called an internet port. An internet port is a number between 0 and 65,000 that represents what the receiving computer is supposed to do with that packet when it gets it. It should be noted that internet ports do not refer to plugs in the back of the machine. No, they're just a number. Sometimes you can use that number. You can have an internet address : number. A lot of times you'll see a test systems, and it'll be www.acme.com:8080 or something. And that will send it to a different port. By default, web stuff goes to port 80. There's a whole bunch of other well-known ports, but web stuff goes to port 80. But you can specify individual ports if you don't like port 80. So applications, when you're running a program that's going to talk to the web, like a web server, it will say what port number it wants to use. If it's a web server, it will say, I want to use port 80. And everything comes in with an 80 as the port number, give it to me. There's others for TCP and FTP, or not TCP, for FTP, for Telnet, for all sorts of other web services that you might have. As I mentioned, port 80 is the service that you usually find for default for web servers. That's for HTTP. If it's going to HTTPS, which most systems use, it goes to port 443. It's a different port number. And again, you can always specify a separate port. You to acme.com: put a port number in here, and that's if they have a usually experimental system that they've booted up and they're running that at that port of that machine. They may also be running the regular system, www.acme.com/file. And that would go to port 80. but they might have something special. Do that a lot if you're testing something, trying something out. Now, that's the internet protocol, the low level of the internet. Again, best effort packet delivery, which is not always the service that everybody wants. There are two big protocols that run on top of that. Actually, there's dozens of protocols that are on top of it, but the ones that account for 99% of all the network are the Transmission Control Protocol, TCP, which you've probably heard of. They usually talk about TCP/IP. Well, that's really TCP/IP. It's Transmission Control Protocol on top of the Internet Protocol, IP. There's also User Datagram Protocol, UDP, that's used a lot. It has different, they're quite a bit different. TCP, that everybody uses, is connection oriented. Once you send something to your web server, you can send multiple packets to that web server without having to reconnect again. UDP is connectionless. Because it's connectionless, you have to put an address on every packet. TCP is reliable. They build reliability on top of the unreliable internet protocol. They correct lost packages. They fix any errors. If things are out of order, they put them back in order. It's very simple. The TCP header just has sequential numbers on it. And if you get a packet that's not out of order, it puts them back into order when it gets them all. Or if it doesn't get one, sends a message back to the source saying, I missed packet 47, send it to me again. And it starts sending those packets again so you can put them all in order. It has checksums to make sure they haven't been corrupted. And so with TCP, you can send things and be pretty assured that the packets arrive reliably, without corruption, out of order. UDP, oh, it does the best effort. The advantage, of course, why would you want to do this when things might be lost, out of order, corrupted? Well, it can do nothing very fast. It takes overhead to provide reliability and these other things. There's almost no overhead to UDP because it doesn't do anything. So it's much faster. And sometimes you don't need all that. If you're sending a message to a domain name server, you can use UDP. It's one message there, they send one message back, that's it. It avoids, there's a bunch of packets required to setting up. You gotta send a message there, send a message back, connect. You don't have to do that with UDP, just send the message. Both of them communicate in both directions. TCP is point to point, that is, I connect to a web server, I send messages to it sends messages back to me. The web server can make other point-to-point TCP connections, but under my TCP connection, I'm connected to one. UDP can go one to many, many to one, however you like it. Again, TCP is stream interface. That means it just sends a series of bytes, and the network puts them all together. When it gets to the other side, it's just a whole bunch of bytes. Doesn't matter how you broke it up into packets, it'll put it all together into one big stream of bytes on the other side. UDP, no, UDP sends back packets, datagrams, sends one message, and you get a message. Most applications use TCP, particularly the web, which uses HTTP, the Hypertext Transport Protocol, Telnet, FTP, most other network activities that wants reliable communications. If you want to make sure messages get there reliably, then almost everybody uses TCP. Other things can use UDP, domain name server requests. If you don't get what you want, just send it again. Streaming audio and streaming video often use UDP because TCP has to wait. If you don't get a packet, it waits for a while until the packet decides that packet's lost, sends a message back, say, I didn't get this packet, and then it sends it again. So there's that pause. It waits for that packet. UDP doesn't. UDP keeps sending them all the time. If a packet gets lost, too bad. Turns out humans don't worry about missing an individual packet. If you're getting music streamed down to you and one packet goes, your ear can hardly hear that. You hardly notice. But if it's going over TCP, and TCP has to pause, wait for this to time out until it decides no packets are coming, send a message back, that you might hear. That's a pause you might hear. So they use UDP. And to avoid the pauses, they often buffer things. In other words, they wait till they get about 100, I don't know, however many packets, bunch of packets, and then they start displaying the information or putting it through your speakers. You can imagine a queue. There are going out, getting packets off the network as fast as they can, sticking them in one end of the queue, and then they're pulling them off the other end of the queue as fast as they need to display the information on the screen or put it on your speakers. If it slows down a little bit on the network side, if they miss a packet, it just slows down. It slows down. Queue gets shorter, but hopefully it can catch up later on by putting more in. If the queue drops down to nothing, that's when you see the little hourglass waiting for its buffering. Another type of protocol besides TCP and UDP is the Internet Control Message Protocol, ICMP. ICMP is not used to send messages from computer to computer. It's there to manage the network. It's there to send messages from computer to computer to keep the network running efficiently. It reports errors, reports network routing issues. All sorts of problems can be used and managed with ICMP. And again, it's there to manage full network. It doesn't fix individual packets. It's there to fix the whole thing. There are multiple things. There's a ping protocol. Ping says, you just send a message out to another computer. When it gets it, it just responds back. Ping is a very simple program for seeing, do I have connectivity to this network? You type ping space www.acme.com. It sends a packet to acme.com. Acme sends a packet back, and your ping will tell you that it got it. It also times it and tells you how fast it got it. And it sends several packets and tells you if you're losing any, so you have an idea of the network effectiveness. By the way, some systems block ICMP packets for reasons we'll get to in just a minute. Ping doesn't work at AT&T. Oh, you can find out how it's going to get there. You might want to know what route the packet is getting. Is there a better route? If you send a message to a router on your network, say your network has two routers, you send it to one router, but that's not the best router. That router will forward it to the other router, but it'll also send a reply back to your computer, an ICMP message saying, in the future, use this router to get there. Also can be used to control the rate at which packets are sent. There's other protocols. TCP has rate flow control, but so does ICMP. And other information that you might want to get. All sorts of things you might do to keep the network running. And there are, of course, threats. Since it doesn't, you could falsely redirect packets to the wrong location. It's an ICMP message saying, oh, if you want to send it to acme.com, send it over there. Well, over there might not be the right place to go. Many networks are sure about ICMP packets. They don't allow them to come into their network or go out of the network. AT&T is one. The Echo protocol will work for a computer on your local network or usually in your building. But if it has to go through a router, the routers also have security systems built onto them, firewalls, and they will stop ICMP messages. Okay, let's skip this question because we're running out of time. Which are connection-oriented? Only TCP. TCP is the only connection-oriented network. Internet Protocol and UDP are best effort. It just sends the packet out there. If it gets there, that's great. If it doesn't get there, it doesn't try to fix that. TCP fixes that. Transport layer security. This is a system used to provide security, encryption over the network. If you use HTTPS, the S is secure, it's going to use TLS, transport layer security. This replaces SSL secure socket layers. It was out there a few years ago. Now SSL is deprecated. You should be using TLS, which is more secure. Basically, it encrypts everything going. Let's talk about how that works. It's a hybrid encryption. It starts off with RSA. You want to connect, you send a request to the server sends back and says, oh, yes, here is a random number that you can use, and you can send things with the public key. Servers have, if a server is going to use HTTPS, it must have a certificate, it must have a public key and a private key, and you can use that to encrypt things with the RSA. Again, RSA is much, much slower than AES, but it doesn't matter. We've talked about hybrid encryption before. You just encrypt a key with the RSA protocol, send it to the other side, they decrypt it. Now you've both got a key that you sent across the network securely, it was encrypted. Now after that, you use AES, which is much faster, the key you just used. Also has the advantage that every connection you make uses a new key. So they can't just keep looking at old things. Maybe if they finally break a key somehow, it won't work the next time. Firewalls. So real quickly talk about firewalls. Firewalls usually between your local area network and the internet. There's a box. Usually the box is built inside a router, and the firewall filters messages, keeps the bad stuff from coming in or going out. Firewalls can be done either hardware or software. A lot of systems that have a lot of packets going through, like AT&T, all the packets on campus go out one tube to go to the internet. And that tube does the routing, and it has assortment of firewalls built into it that look for bad traffic. This is usually hardware boxes because they want it to run very fast because it has to check all the many packets coming into the network. You can often they're built into routers because the packet's going to be going into a router. But sometimes they have separate boxes. Often they are hardware and software. There are different types of firewalls based on what level you're going to. If you're just going to do network layer, at a low level, you can do packet filter. That's just based on where is it supposed to go. You might decide, I don't want anything coming into my network from that. I don't want anything from www.evil.com. I've got evil.com's IP address, and I just say no. Nothing can come from that address. And so if anything comes, it's going to, usually if something comes in and it's not going to, doesn't like it, it just drops it. Doesn't tell the site that I didn't send it, just drops it. Doesn't do anything. It doesn't get in, nobody tells it. Circuit layer is a transport layer, is often used like for email and stuff. And there's application servers. Application filters, by email would be an application level filter. And then there's network address translation proxies. I think we'll get to that, maybe. Again, packet filtering, it just looks at where the packet's going, coming and going, and you can configure these things. If you have Microsoft Windows or Linux or Apple Mac OS, they come with firewalls built into the computer. Usually the way it's configured is good enough most of the time. If you want to do something extra, you can go out and add filter requests to that. If you're getting something from a site and you don't want to get anything from that site, you can go into your firewall and say block it, and you'll never get through the firewall. Again, you can filter on all sorts of things. The source IP address, although note that that can be forced. Just because it says it comes from 152.8.247.5 doesn't mean it really came from that. It's just a number in the packet. A malicious system could put that address there. Now, they'd have to have control of the computer such that they can send packets with bad addresses, but that they can do. You can filter based on where it's supposed to go. You might say, I'm going to allow things to go to my web server, but nothing else. Port numbers, again, port number decides, is this going to go to port 80 for the web server, or are we going to someplace else? Why do we want to go to someplace else? We're not going to allow that. What even protocol are you going to use? You could filter by the application. Is this a web server? Is it FTP, Telnet? Are we going to allow those or not? Serving web firewalls are effective. Here at A&T, we have big advanced firewalls for email and other systems. They filter out lots of stuff that are sent to A&T. I don't know the percentage of packets that are dropped. Anybody know how much is filtered out? At one point, it was like 80%. 80% of the stuff that came into the A&T network was dropped. Never got to where it was going because you didn't want it to get to where it was going. It was stuff that you didn't want to see. So they dropped it all. Circuit level, circuits, connections. works for TCP, and decide TCP is connected. And again, as I mentioned, there are default configurations, and you can adjust the configuration as you see fit. If you have a commercial system, they will be adjusting the configurations all the time, depending on what's happening. Most systems try to protect the perimeter. That is, the packets coming into the network from the internet or those going out. It's usually okay. You can send packets all around the inside the network, but you can't go out, you can't come in without certain controls. Some systems will have what they call a demilitarized zone or perimeter network. They'll have firewalls to protect the network, but outside of that firewall system, maybe second layer firewalls, they'll have servers that are publicly available. You might have your web server outside your network. It is still part of it. Imagine packets come in, they go through a first router and a first firewall. It says, okay, coming here. And then if you're going to the web server, that's okay. You can get to the web server there. But if you're going to go to other computers in your company, you have to go through a second firewall. Most things don't go through the second firewall. That allows the general public to see your domain name server and to see your web server, but nothing else. They can't get to your other computers. Oh, yeah. Windows firewall, I think I mentioned that. It's an important big question, of course. How do you know a bad packet? How do you know something is coming in that's bad? A lot of commercial systems have firewalls that are constantly updated as the firewall company recognizes new threats. They'll send updates out to your firewall to say, nope, start blocking this. Hardly ever they take off packets, but they'll continue to add more filters. Like I mentioned, emails, yes. 2007, 97% of all emails were unwanted. Now it's down to 45%. We're getting a lot better, you'd think. But I don't know about you, but I get a whole lot of spam messages every day. The elections had not helped that at all. I get messages telling me to vote for somebody all the time. Actually, no, they're telling me to send money. All these candidates are like junkies. You give them something, they just want more, more, more. So, yes, I got 21 political ads earlier last week, each day, and probably more. Now, one of the things your network can do to prove security is network address translation. That is when the router that connects to the internet uses different addresses between the router and the internet, and then the local addresses inside. There are a set of addresses that are special only for using on an intranet inside your network. So your computer on your network, here at A&T, we do, I think the addresses have a 192 or a 10. I don't remember what they are. Suppose you go out and look, but I don't remember. But the address, internal address. That's not the address that you say. So if I send a request to www.acme.com to the web server, it will get the message, but it won't see this as the return address. Instead, it will see the router's return address. The router keeps the table. If I send a request out to acme.com, it keeps a table saying, oh, my computer is connecting to acme.com. If something comes back from acme.com on this connection, then change the address and send it off to my computer. So the other computers don't know anything about inside of my network. It keeps inside your network. So nobody can send a packet to anybody inside the network because they don't know the addresses there. They can try to guess. Mind you, there are 16 million addresses starting with 10, so it's a lot of guessing. Although there's only 65,000 for 192.168.0. So that you could guess. Another advantage of network address translation is that we're running out of addresses. Again, there's only 32 bits for address. That's about 2 billion possible addresses. But the network address translation allows one network to use one address and support thousands of computers. That's what we do here at A&T. Internet Protocol version 6 uses big bits, so that's not as much of a problem. Oh, we're almost done here. How are we doing for time? Oh, we're not gonna make it. All right, it is time's up. Will not do this question. What does, the answer is all of these firewalls, network actors, translation, demilitarized zones, all help keep attackers out of your network. We'll continue with the rest of the stuff on Wednesday. Real quickly, remember that there's an assignment out there. It's due by noon next week. You want to get started on that. We talked about dark web. You'll need to go out and access. And note that this assignment will appear on Blackboard twice because the stuff that you have to put on Blackboard, which is the dark web portion and the script injection, goes to Blackboard. The things that go to the web server, the web server keeps track that when you succeed, it keeps track of your address. You have to use the last 4 digits of your ID number, your university ID. Use the right numbers because that's how I know it's you. And then the server will just put that in the database. And sometime shortly after noon on Tuesday, I just dump the results of that database and give everybody credit. Whereas I'll have to have the TAs go through Blackboard and give everybody credit. Okay, that's it. Any questions? I do have.
Have to download.
Yes, you need to download the Tor browser. And I need to talk to this one student. Okay. Let me know if there's any problems.
Yeah. Why do I just now realize
How about that? I can't work.
the air pump? That.
Trying to
Yeah.
agree.
I'm afraid of not.
Agree.
Yeah. I'm glad you don't play next week because no one they'll still find a way to let it down. No one has lived how this year's been going. Fire the head coach. Yeah.